Let's continue our example here, 5.12, looking at a skier on a slope. We were solving for her acceleration if the friction is negligible. So let me go ahead and do that into my calculator, and we get that our acceleration is 4.14 meters per second squared. Again, that is saying that the friction is negligible. Okay, now if in part B we want to find her acceleration again, but we do have a friction involved. Okay, so now our net force will again be equals to MA, and we have our X component of the weight, but now we have that friction involved. So let's go ahead and solve for our acceleration here. So we have acceleration equals our weight in the X direction minus our force over our mass. Okay, or let's see, mg sine theta minus F over m. Okay, and we can go ahead and plug in our values. So we have m is 60 kilograms, g is 9.8 meters per second squared, sine of 25 degrees minus our friction, which is 45 newtons, divided by 60 kilograms. So I'll go ahead and put that into my calculator. And I get an acceleration now of 3.40 meters per second squared. Okay, and that does make sense because we have a friction involved, so it should be less than when the friction was negligible. Okay, all right, moving on, just to get the idea of the normal force that's experienced by an object resting on an inclined plane. Okay, so the normal force is then calculated as mg cosine theta, okay, because it's going to be equal and opposite to the weight, the y component of the weight. Okay, so this is just a diagram showing you the trigonometry behind that idea. Okay, so again, our normal force would be in this direction. Okay, all right. Here is another type of force. This is going to be tension, and that's the force along the length of a medium. It is a pulling force that acts along a stretched, flexible connector, like a rope or a cable. Okay, and we calculate it in a similar way. Okay, T, or tension, is equal to the object's weight, or mg. Okay, so this is an example of this. We have someone holding on to a weight that's attached to a rope. Okay, so there's tension in the rope, and this is how we would typically draw the forces involved here. Okay, and this would be the free body diagram of the mass here. Okay, and I have a couple of other examples here. Okay, we have tension in different tendons and muscles. Okay, and then tension with wire. Okay, all right, so let's look at an example of this. So here we want to calculate the tension in the wire, supporting a tightrope walker who has a mass of 70 kilograms and is shown here. Okay, So this one maybe seems simple at first, but it is a little bit involved, okay? So what we will do is first break these down into their components. So we have, let's focus on the left side here first. We have this tiny little angle here, right there, okay. And due to trig, we know that this is going to be the same angle as this. Okay, I forget what property that is, so that's 5 degrees. And this is T sub L. Okay, and so we will have a y component here and an x component here. So we have T, L, comma, x, I'll say, and T, L, comma, y. Okay, and we have a similar one on the right side. This is TR. Okay. And again, 5 degrees here. And we have TR, comma, x and TR, comma, y. Okay. And then our weight is just in that negative y direction. So if we want to try to draw all of this in one diagram, I'm going to make it a little bigger. Okay. This is how we would represent it. So we have T sub y, okay, or T sub ly, I'll start with that one, and it's going to be at this little height. So I'm going to mark it right about here. That's going to be an arrow, and that's going to be T L sub y. Okay. Then we have, on this side, we have TRY, and that's about the same length here. So I'll try to make it as even as possible. So let's say it's that much. Okay, so it's like we're adding the two components together here. Okay, so we have TRY. Okay, then we have on our x-axis, we have TLX. That's about there, I'd say. And TRX, about there. And it doesn't have to be perfect, as you can see, this is not perfect. And now you notice that this wire is holding this person up. So logically, the tension in the y direction must be strong enough to hold the weight of the person, right? So it should be equal and opposite to that weight. So this is going to be W. Okay? And that's just in the y direction. So this is y, this is x. Okay, so now this is our little diagram of this situation that we have here. Okay? So we want to find the tension in the wire. Okay? So, we want to create, let's see. So again, I said that our tension should be equal to our weight, right? So let's start with that idea. So F net should equal to T L y, that's going to be the y direction, plus TRY minus W. Okay. And we notice that this person is still, so we're going to say that this is a, not stationary. I'll think of the word here in a minute. And so if there's no motion, if there's a constant velocity, or if there's no velocity, our acceleration is 0. Okay, so if this person is not moving, remember that F net is equal to ma. So if a equals 0, our force is equal to 0. Okay, so therefore in this equation here, our F net is equal to 0. Okay? Alright, so that's our first equation. Now we can build our second one in the x direction. Okay, we have a positive TR comma x and a negative TL comma x, and that is it. Okay. Alright, so we now have this equation that we can manipulate a little bit. So our TR sub x is going to be equal to, let's see, we are going to have the adjacent over the hypotenuse, so that's going to be cosine, right? So we have TR cosine of 5 degrees minus, same thing over here, TL times cosine of 5 degrees. Okay, again, that equals 0. So now we can say that T sub R is equal to T sub L. Okay. Or we can say that is the tension T. Okay. So now let's take this equation and see if we can find another relation here. Okay, so we have T sub Ly, which is going to be TL times the sine of 5 degrees plus TR sine of 5 degrees minus the weight, which for now we'll leave as W, equals 0. Okay, we determined that TR and TL are the same, so we can just call them T. So if we add them together, it's going to be 2T sine 5 degrees minus W equals 0. Give me 1 second. I'm going to go ahead and add another page here. All right, so let's go ahead and continue this. We now have the weight is equal to 2T sine 5 degrees. Okay, yeah. And we want, again, we're looking for the tension. So let's go ahead and solve for T. So that'll equal W over 2 sine 5 degrees. And remember that weight is equal to mass times acceleration due to gravity. So if we plug that in, our mass is 70 kilograms times gravity 9.8 meters per second squared over 2 times sine 5 degrees. Plug that into our calculators. 8 divided by 2 sine 5. Our tension on the rope is 3,940 newtons. Okay, this is our total tension, or just the tension of the rope. All right, we'll continue this discussion in our next video.